So again, you won't need that paper that you're getting right now. You won't need that just yet. We'll get started on the other stuff first here. All righty. Okay, so you just throw them right there, it's fine. So we're going to talk about evaluating functions. Okay, something you've been doing probably for a very long time in your mathematical career. So I won't dilly-dally too much on this stuff. But let's just start with a basic function here. F of x equals like x squared minus 3x plus 2. Okay, a function, right? Quadratic function. Not so easy to determine the transformations that are happening here, right? Because we don't really have, I mean, we can see our parent function is going to be x squared because there it is right there. But then this minus 3x, that kind of throws things off a little bit for us, right? We're like, well, how does that really show a transformation there? Now this plus 2, well, we know that's going to be what kind of transformation there? And so up to, yeah, and we're gonna potentially still have that that up to, but maybe or maybe not. Okay, actually, if you wanted to get the full kind of like effect of what's happening here, you would actually need to complete the square, and you could then see the kind of transformations and stuff like that. Okay, to see like whether it's really right or left, and then up or down at all, and stuff like that. Okay, but we do see kind of that up to there. But looking at that, I think actually we would have. Yeah, it wouldn't be just, it looks like it's up 2, but it actually would not be just up 2. Once you complete the square, you would be able to see what it would actually be shifted up or down or left or right, stuff like that. Okay, but that's not what we're worried about right now. Okay, we're worried about just evaluating stuff. So, I'll start out super basic here. Something like we should be able to do something like evaluate. Okay, and we'll do something like f of 3, like that. So now what we had here is this rule, right? This function rule that has this item or object called the function f. And when we apply f to the variable x, we take the x and square it, we subtract 3 times that x, and we add 2. So then with replacing, we're still using the object, the function f here, using that, but instead of an x, we're now going to have a 3. So wherever we had the x before, a 3 will replace it, right? So it'll be 3 squared minus 3 times 3 plus 2 like that, right? So the 3 replaces that x. It's plugged in, we say sometimes, substituted. Okay, and so you get 9, take away 9, 0 plus 2, so you get 2. Right, easy enough. But that's not all, right? We don't always just plug in numbers. We can plug in other things. For example, we can plug in expressions. So for example, f of 2x. Right, so this is now an expression. It's an algebraic expression because we have a 2 and an x there. Right. But the same kind of idea applies. The function applied to x means we just take that x and square it. We subtract 3 times that x and we add 2. So here, now we're going to apply this function f to 2x. And so what's it going to result in? Well, it'll be 2x quantity squared minus 3 times the quantity 2x plus 2. So whatever goes in those parentheses here that we apply the function to replaces the x's in the other spots. And we can simplify this as well. 4x squared minus 6x plus 2. And yeah, there's a GCF and maybe factors, but we don't need to worry about that right now. Just that's all we have to do, simplify. Okay, so take 2 seconds here and try these. All right, so I'll give you like a C. Evaluate f of -1, please. And then D, I'd like you to evaluate f of 2 plus f of x minus 3. Okay, so try those both. I'll kind of walk around and help here too. And you do as much mental math as you feel comfortable or confident with there. So don't feel like you have to write out all the steps or anything. actually is, and then just add your two answers together. That's what I'm going to do. Yes, not quite. Constant term there is a little off. Oh, Jeff, you're back. Are you doing? Do you need help with anything, or are you okay? Okay. Tired? Yeah. What happened?
I took
party last night.
No, I accidentally took some extra medicine this morning.
Oh, I'm sorry to hear that. God, and you don't have your normal monster here. You just have your light mango mash. That's probably not going to be as energetic. Well, maybe that'll help. Or maybe not. I don't know. All right. Well, if you need to like go to get a drink of water or something like that to the blood flow, and just say so or something like that. All right.
So we got 2x.
Is the party lit at least?
There was no party. There was no party.
I thought you said it was twice.
I'm gonna give you like one more minute here. One more minute. One more minute. And then we'll go over these two. Ooh, here. I'm also going to pass around the homework paper. I need to get in the habit of doing that. It's not part of my programming right now. So again, just find your name on the homework paper and then put, a score out of 10, based on how much you got right, you think. Okay, that's all you got to do. And you can just estimate it too. If you didn't do anything, that's fine. Just put a 0. Okay, and I just pass it around here. We'll make sure everyone gets it. Okay. And make sure you put it under the correct date too, so the 12th. All right. While that's going around, let's go ahead and go over this here too. So, Ethan, you got an answer for us for letter C.
Letter C.
Letter C.
I got
2. We all agree? 2. 7. 6. Do I hear 5? No. So 2, 7, 6. Anything else? All right, that's a lot. That's a lot. All right. So, well, let's see here. Anyone want to volunteer and talk us through how they did it?
I mean, I'll go.
3 different answers. All right, go for it, Ethan.
So negative 1 squared is 1.
Negative 1 squared. Okay, it's going to give us 1.
Negative 3 times negative 1 is plus 3.
Positive 3. Very good so far.
Oh, I have minus 2.
Okay, so you miswrote the problem. That is going to affect things. So the answer should be 6. That's right. So nay, nay, yay. Okay. All right, 6 is the answer, and the answer is 6. Any questions about that? Okay. Do be careful typing this in your calculator. If you typed in negative 1 squared minus 3 times negative 1 plus 2, well, in that case, you got 4. Okay, well, you can't see. There we go. Okay. So make sure you put parentheses around that negative 1 if you're going to type in your calculator. And then you get the correct answer of 6. Okay? So, okay, that was fun. All right, now we'll try letter D. We'll see. This one's more complex, so we'll see how we did. All right, let's go to. Oh, we already heard from Daniel. Let's pick somebody else here. Grant. What do you say, Grant? Final answer here. What'd you get? It's kind of weird. Okay. Do you want to share it?
Sure.
All right, that's the spirit.
X squared minus 9x plus 20?
X squared minus 9x plus 20? All right. Anyone Anyone get a different answer than that? Think that they're right?
I mean, I did, but because I wrote the problem.
Oh, right. That's going to mess it up, yes. Yes.
I don't know if I'm right.
Okay.
I wrote
I got x squared minus 3x plus 18.
Okay. X squared minus 3x plus 18. All right. Well, I'll give Grant the first opportunity here to explain himself. So, Grant, how did you go about doing this?
Well, f of 2 is 0.
F of 2 is 0. Yes, let's just verify that here. 2 squared is 4. Minus 6 is going to be negative 2. Plus 2 is 0. So, yes, that is going to give us 0 there. Oh, okay. You wish to retract your answer. That's fine.
So then,
But continue, yeah, please.
f of x minus 3, so it's x minus 3 squared, which is x squared minus 6x plus 9.
Okay, good. Uh-huh.
And then it's a minus 3 times x minus 3.
Uh-huh.
So you get minus 3x plus 9.
Uh-huh.
And then you add 2.
And then the plus 2 at the end there from the function. That's right. Very good. Combine like terms. X squared minus 9x, 9, and 9 is 18, plus 2 is 20. So you're right. Well done there. Yes, Jen.
Why is the f 2 0?
F of 2 is 0, so if we plug the 2 in here, 2 squared is 4. 3 times 2 is 6, so 4 minus 6. 4 minus 6, negative 2, plus 2, 0. Okay. So, right, something we've been doing for a very long time, right? There's still possibility for little errors, right? We got arithmetic we got to make sure we're doing right. We got to make sure we're expanding things and, combining terms correctly. So it gets a little twisty and turny in there, but so just be on your toes, right? This is something we've been doing for a long time, but it still can be a little tricky. All right, but that's enough of that. Let's move on to some special kind of functions. And they're not really like, I'm not grouping them together for any particular reason other than they're just, kind of different functions than what you're used to seeing, okay? So one of those kind of different kind of functions are your sometimes called compound, but typically called piecewise functions.
That's they're written differently, and it's for each bracket of x values. It's a different function.
Typically, yeah, exactly right. Yep, exactly right. Yep, it's kind of like a Frankenstein. It's made up of different parts of other functions. All right. So we'll do a quick example here. Well, just write one out. All right. So piecewise functions can be as complex as the author, wants them to be. Okay. So in this particular case, we'll keep it kind of simple, and we'll just do 2 pieces. Thank you. Anyone else need to fill out their homework information here? Okay. Yes, you did. Okay. And for x less than 0, and for x greater than or equal to 0. Okay. So one thing to note here about piecewise functions is that we've got parts, right? And each of these parts are true, or we only consider those parts for a particular x value. So for example, the function f is x squared plus 1 only for x values less than 0. The function f is 3x minus 1, so kind of forgetting the x squared. It's 3x minus 1 for the other x values when x is greater than or equal to 0. Okay? Bless you. You'll notice here, these x values, these intervals, I guess, for x, do they overlap at all? No. Will they ever overlap? Or should they ever overlap? No, why not? If they overlap, what's going to be true? Or what's the problem with them overlapping?
It won't be a function.
It won't be a function. Exactly right. Okay? So key word here, right? We're calling this a piecewise function. And so these x intervals should never overlap. They should, they should join up. Well, they don't have to join up. But they may join up, they may not. But anyway, they definitely won't overlap each other. Okay? So that'll come into effect later, all right? When you're graphing these piecewise functions today, make sure that they pass the vertical line test, right? Because if they don't pass the vertical line test, it's not a function, all right? And also, if you're writing piecewise functions from a graph, again, make sure your intervals don't overlap. Sometimes you have a choice about whether you make this one the equal to, whether you make this one here the equal to, or this one the equal to. You can have some choice if those points kind of join up. You can pick and choose which one you want, but they should never overlap, though, right? Okay. So again, we won't be spend too much time here, but let's just worry about evaluating for right now. We'll come back to graphing. So let's just again say evaluate, and I don't know, I'll just have you guys try here. So let's do f of 6 and figure out what that is, and then also evaluate f of negative 3 and figure out what that is, and then also f of 0. So take like a couple seconds there, figure those out. What f of 6 is, what f of negative 3 is, and what f of 0 is, based on that new piecewise function that we defined here. Question? Okay. If you wanted to check your homework in the meantime while you're like doing the notes and stuff, let us know. Okay. Question? You need a paper. Yep, I'll get you one. Sorry. Very good. So f of 6. So you'll see here that the 6 is replacing x. So the x value here for this particular thing is 6. Okay, so if x is 6, which piecewise function, that should be an x there, not a y. Sorry. It's my handwriting. And so which piece of the piecewise function do you plug a 6 into? Which one? That was my question. These aren't part of the function. They're kind of like, they are restrictions. So the function is only equal to this for x values that are less than 0. Well, 6 is not less than 0, so we're not going to use this piece. Right? But 6 is greater than or equal to 0, so you use that piece. Okay. Let's give you like 15 more seconds here. All right. So, Adrian, what do you say for letter A, f of 6? What'd you get?
When I put it into the top one, I got 57.
Mm-hmm.
And it didn't work because x has to be less than 0.
Right. So you can throw that one out.
And another one, I got 17.
Uh-huh. And that one does work, right? Because the x value here is greater than or equal to 0. Yeah. So we'll just plug the 6 in to the bottom part, and that'll give us that 17. Okay. So yeah, don't even worry. Don't even worry about, I mean, what I suggest you do, discern which function, which part of your piecewise function you're going to plug your number into, and then just plug it into that. Don't worry about plugging it into both, and then, crossing out ones that aren't supposed to work or whatever. Just worry about the piece that you're supposed to plug into and plug it in there. Okay, just do that. But that was right. So good job there. Okay. All right, May, letter B. What do you say? F of negative 3. What's that going to equal? 10. Okay, so which part of the piecewise function did that go into? The first one, the top part right there. Yeah, so that would be negative 3 quantity squared plus 1, and so that gives us the 10 there. Very good. All right, and then let's go to... Wait.
For A.
A.
Isn't that x squared?
This is, but notice this piece is only true for x values less than 0. Is 6 less than 0?
Oh.
So you don't use the top piece, you want to use the
I
bottom.
got them mixed up.
Gotcha.
I did it.
Oh, your signs were,
reversed.
okay, gotcha. Okay.
I did it completely reversed.
Yep, that'll do it then. All right, so let's go to Chrissy for letter C, f of 0. What'd you get? Negative 1. Again, and that should go into which piece? The 0,
I did get that one right.
Bottom piece. Good. Good. That's what you should do, because it's exactly 0, so it goes in that bottom piece. All right, easy peasy. Next. So that's compound piecewise. We'll come back to those, talk about graphing them in just a second. But for right now, I want to talk about one other kind of special function, which isn't really related to compound or piecewise necessarily, but it's kind of like a form. And this thing is called the difference quotient. Okay? And for those of you that are planning on taking calculus in your future, be it here or in college, okay, this is like fundamental to about half of the calculus that you're going to be doing. Believe it or not, okay, this little calculation with a limit thrown in front of it, and we'll talk about limits later, is fundamental to about half of calculus. So let me show you what the setup is for a difference quotient. And it's nothing really fancy. It's just taking your function, whatever that happens to be, evaluating it at x plus h, subtracting the original function, f of x, from that, and then dividing that all by the variable h. Okay? So there's two variables that you're going to have when you evaluate a difference quotient, x's and h's. Oh, right, yes. Thank you for saying that. Does anyone else need to know about when their times are for pictures today?
Mine's 10 o'clock.
You got it, okay? All right. Yes, Jeff, you have a question?
Isn't there two types of calculus that were invented by two different people?
Yes.
Isaac Newton invented one, and some German guy that
yes.
had a really hard to pronounce
I think
name.
like Leibniz or something like that. Yeah. So right. So this one I'm talking about is referring to the
Which
one
one
that
did Isaac Newton invent?
this part of it, I would say, differential. Yeah. Mm-hmm. Yes. And then the integral stuff is developed more, I think, by the other guy. But yes. So this is something that you would use in the differential part of calculus. Okay? So difference quotient. What makes a difference? There's subtraction. What makes it a quotient? There's division. Okay? So, but that's, the name isn't so important. It's more like, can we evaluate? So a difference quotient is something you do to a function. All right? So this gets tricky for students. And I think it's because there's kind of like several substitutions you have to do. Okay? So let's say we're going to apply, apply the dq to f. Okay, so that's what we're going to do. We're going to apply the difference quotient to f. We're going to take f, put it into that difference quotient there, and simplify. See if it simplifies at all. Okay, so question, Jenna.
What is, there's like a comma.
Yes.
The h thing.
H not equal to 0.
Oh, okay.
It's a little, and this is kind of like pedantic / overly detailed maybe thing that sometimes mathematicians do throw in. But why is it important here that we state that h is not equal to 0? We don't want to divide by 0. Exactly right. So, h being a variable, it technically could be any number, but we put a little comma here and saying, well, it can't be 0, so then we're okay.
Which number do we plug in from the f of x into h?
Right. So actually, our final answer is going to have things in terms of x and h. So it's going to have x's and h's in there. So we're actually taking something that's relatively simple, this function, and they're going to make it more complex. Okay, but it'll actually simplify nicely here. So let's just take it piece by piece. All right, this first piece of the difference quotient, we have to figure out what f of x plus h is. Well, I know what f of x is, so I can just I'll do a little side calculation here before I do the main one. And I'll figure out what f of x plus h is. It'll just be 2 parentheses x plus h, and then plus 3. Right? I'm just replacing the x with x plus h like that. Which, if I simplified it, is going to be 2x plus 2h plus 3, like that. Okay? And now, again, to evaluate this different quotient, do we know what f of x plus h is? Yeah, 2x plus 2h plus 3. Do we know what f of x is? Yeah, 2x plus 3. And then we can divide it all by h. So here we go. We're going to now apply the difference quotient. So I'll rewrite f of x plus h minus f of x all over h. And now I'm going to put the f of x plus h part in. So it'll be 2x plus 2h plus 3. Okay, so I substituted that in. Minus the f of x part, which is 2x plus 3, all over h. Like that. Okay. Okay. And then from here, what can we do to simplify?
Multiply everything by h.
So, well, this is not an equation, though. We're just trying to simplify this expression. Distribute a minus here, right? We can distribute the minus sign. So here we got 2x plus 2h plus 3. Did you make it in time, Brendan?
Yeah.
Okay, that's good. Oh, good. So that's all right. Very good. All right? Distribute the minus sign. Now what can we do? What cancels? The 2x's do. What else? The 3's. And so we're left with 2h in the numerator over h. But wait, now what cancels? The h's. And so we're left with just 2. That's right. Just 2. And there's a reason for it. There's a meaning for that. But we're not going to go into that just yet. I promise we'll come back to it later, though, in this class. And not this one right now, but later, days from now kind of thing. And we'll get some meaning behind it. But for right now, we just have this weird thing that resulted in a 2. Okay? So questions on any of that? Yes?
In real life, what is this used for?
So this is used to find the slope or the rate of change of a function.
Oh yeah, that's how you find the slope of something that's not a linear function.
Right. So like right now, the best we can do, right, with what you guys kind of know, is to find the slope of a linear function. Why? Because the slope of a linear function, it stays the same, right? Anywhere you are on the line, the slope's always the same thing. However, when you have other functions that are more like curvy and stuff like that, it turns out you can actually find the slopes of those functions. It's just the slopes are changing depending on where you are. Sure, like sine and cosine, like quadratics and stuff like that. And so they all, all these curves have different slopes. And so this allows you to find the rate of change of a curve at a single point. So again, which is kind of mind-blowing, because how many points does it take for you guys to find the slope of a line? You need to have 2, right? But this actually allows you to find the slope using a single point. At a single point, I should say. So, yep. Question?
As for where it's exactly used in real life, my teacher back in Mississippi had a poster saying which jobs would use.
I used to have a poster like that too. Yeah.
And really, the only one that uses absolutely everything is like architects will use some.
Yep.
Like most types of science and computer jobs will use some. Like the field I'm going into I need to know matrix math to do that. So,
yep. Linear algebra is the name of that branch.
Yep. And but really, the only profession that uses basically every type of math taught in high school
is a math teacher. No, I'm just kidding.
Well, yeah, no duh. But a physicist.
And a physicist.
And a physicist.
No, it's true. All right, so let's do one more difference quotient here, but let's make it a little more complex, right? Because why not? That was too easy. All right. So take a look here at the function g of x equals x squared plus 2x minus 6. Now we're going to apply the difference quotient to it. Now, I know it says f of x plus h, but you can just as easily, say g of x plus h minus g of x all over h there, right? It's the same idea, same principle. We're just going to apply this to the function. Okay. It just gets a little more complex, but I'll show you here. So I'm going to, again, I know what g of x is, so I know this piece of the difference quotient, but I need to figure out what this piece is, the g of x plus h piece. So I'm going to do that real quick. Well, or not. We'll see here. So we'll do x plus h squared plus 2 parentheses x plus h minus 6. So I replace all the x's with x plus h's. And then we'll simplify this. So I got to expand out x plus h squared. So it's going to be x squared plus 2xh plus h squared. And then distribute the 2 to x plus 2h, and then minus 6. Because, so again, I took my function here, g of x, okay, which is this piece of the difference quotient, right? I need to figure out this piece as well, though, before I can evaluate the difference quotient. So I'm kind of doing some preliminary work here. So I'm evaluating g of x plus h, okay, just because I see that's something that I need for the difference quotient. I need to know what that is. So I do g of x plus h, and then expand it out. We'll simplify now, combine like terms. So I get, let's see here, x squared plus 2xh. Actually, there's no real like terms to combine, so never mind. We'll just leave it like that. Okay, so there's g of x plus h. There's g of x, and now we'll put into the difference quotient. One sec there. Let me get this finished out here, Jeff, and I'll get your hand, okay? So g of x plus h, x squared plus 2xh plus h squared plus 2x plus 2h minus 6 minus f, or g of x, x squared plus 2x minus 6. Okay. Now, if you're looking at this and you're thinking to yourself, well, I thought about taking calculus, but now this is just too much. All right. Well, you won't be doing this for all of calculus. You'll learn shortcuts and stuff like that too. But you will be doing this to start out at least, just to kind of, get an appreciation for it. But it's really only, if you're taking A to B, C, it'll be like a day or two that you do this, and then you move into shortcuts. Okay? So, don't worry about that. Start with the shortcuts instead. Debatable. Debatable. Because sometimes, on the AP test, you got questions that had it in this format, so you got to be familiar with it, But I hear what you're saying, though. It would be nice. Or if you take certain AP physics, they'll teach you the shortcuts real quick, too. For taking derivatives. Anywho, we've got our setup here. So any questions on just getting to this point? Are we all okay so far? On where everything came from?
So what you're left with is h squared plus 2h over h.
So right, things cancel here, right? So I'm gonna go ahead and just distribute it rather than rewriting it all over. So it'll be minus x squared minus 2x plus 6 like that if I distribute it. And then we have like things that cancel out. So the x squared here will cancel out with the negative x squared. We have a positive 2x and this negative 2x cancel. And then a minus 6 and a plus 6, and those cancel. And so we're left with 2xh plus h squared plus 2h all over h. Okay, like that. Question,
So
Jeff? Sorry,
what
thank
did
you.
you do in the first couple steps to
Up in here, you mean?
yeah? So did you just split the
Split it up.
Why is the 2's only going with one of the x plus h's?
Correct. So it's 2 times x in g of x. So then g of x plus h would be 2x plus h. So then 2 only distributes to the x and the h right there. This x plus h gets squared, so that's where you get that x squared plus 2xh plus h squared from.
Okay, those first two steps still have me lost. I get the last couple, but
So you're from here to here, you're saying?
no, the first.
Right
I mean,
here?
actually, just the first step in that case.
So right here.
The first step.
Here.
No. First
Here.
Step. No, going below that one.
Here.
Yes.
Okay? So we're trying, and again, in an effort to try and make this simpler, what I'm doing is, again, we're evaluating the difference quotient. I already know this piece of the difference quotient. I know what g of x is. That was given to us, right?
Oh, I see.
I wanted to figure out what g of x plus h was.
You plugged in x plus h for every x.
Exactly, because isn't that what you're
makes
supposed to do?
sense. That's what you're supposed to do.
Yes.
I get it.
Yes.
Okay, everything makes sense.
Was there another question? Rose, you have a question? 2xh? That came from when you expanded to x plus h squared there. Okay, when you do x plus h times x plus h. Okay, like FOIL, right, first, x squared, outer, xh, inner, another xh, and then you get the idea, right? Yeah. Okay. Is this the best we can do?
No.
No, what can we still do? How can we cancel out the h, though? Should I just go h and h cancel like that? Well, right. So we can break. So a couple options you can think about here. We can break up the fraction over the addition here and do 2xh over h plus h squared over h plus 2h over h. Or I see there's an h GCF here. We can just factor out. So I'm going to factor out the GCF of h. All over h. And so the h's cancel, and we're left with 2x plus h plus 2 as our final answer there. That's the best we can do. Okay. And again, limited meaning right now for you guys about what this is. I mean, I kind of described it, but it's, there's more to be seen.
Is a linear equation?
It turns out in this case, yes. We started with a quadratic and it went to linear, right? Last one we started with linear and it went to constant. So.
And I think I've heard about this, and shouldn't that linear equation touch on one point?
Yes, tangent, point of tangency. And we'll, again, see more about that later. Okay, let's get these papers out that I gave you. I want to touch on one or two of these here. Okay. For funsies. Oh, right. And did I give you a paper? I never did. Right. Okay. So, 1, 2, 3, 4. We're going to graph here. So, I don't know. Pick one. Which one do you want me to graph? 1, 2, 3, 4. Oh, okay. I heard 4 first. Here we go. Number 4. Okay, so number 4, we're going to take the function, piecewise function there. F of x is 2 pieces. All right, we're going to do x values less than or equal to 2 is that negative 3x plus 6. And then for the square root, we're only going to do x values between 2 and 6. Okay? My recommendation, and again, you can kind of do however you want here, but I like to start with the first function, and I like to start at its kind of like end point. So at 2 in this case, exactly right. Okay? So to graph this then, I'm going to take that 2 and plug it in here. So negative 3 times 2, negative 6, plus 6, 0. Okay? You can even write it out, I guess, if you want to, you know. You make like a little chart for yourself. Something like that. Okay? So we have the point 2, 0, right? So 1, 2, and then 0. Sorry?
Isn't 3x plus 6?
Negative 6, but then don't forget the plus 6 there.
See.
So what kind of dot should I put here at 2, 0? Closed. Why? Because it can be, right, we can be at 2 at 0. It's because we got the equal to, right? So we'll put the filled in dot there.
And another point is just the x-intercept, and that'll give you a good line at 6, or at 0 it's 6.
Right, right. So, yes. So what we can look at then, we want to graph the rest of this, right? All I've got now for that negative 3x plus 6 is this dot, okay? So if you keep your wits about you, you can use, you know, what you know about, well, what kind of graph would this be? Linear. It's a line. So you can use, if you keep your wits about you, you can use, you know, what you know about lines to graph this. So, for example, I've got my point here. I need to go which direction from this point according to my little inequality here? To the left. Okay, I want to go to the left. Now, some things you can use. Jeff said, oh, there's a y-intercept of 6. Is that y-intercept to the left of our point here? It is. So you can use that. So 1, 2, 3, 4, 5, 6. Okay. What else could we have used here besides that y-intercept? What other information are we given? The slope. Okay, it's negative 3. But you got to be careful, right? Since we're going to the left, we have to kind of go the opposite. So instead of going down 3, right 1, right, we're going to go up 3, left 1. So there are some more points there. Up 3, left 1. And then up 3, I'm off the page there. And so then we'll just go to the left and connect those dots.
Could you explain that? Or down?
Sure. So we got this point okay, right?
Yeah.
And you're okay with this point too? So then I also just you could have used the slope here too, because it is a line, okay? But the slope is saying down 3 is negative 3. So that means down 3, right 1 normally.
Yeah.
But if I go down 3, right 1, I'm going to the right. I don't want to go to the right because
Oh.
we got to go less then. So we'll go up 3, left 1, the exact opposite, which will then also get us some more points there. And so there it is. Okay. And we'll draw an arrow because we can keep going, right? We can keep.
Can I finish?
Hold on a second. Okay, so questions on that piece? All right, so then the next piece, Jeff, where should we start? At what point?
So you should start at, well, actually, exactly the same point, I believe.
Yes, so I suggest, even though it doesn't say equal to here, I would still suggest starting at this 2. Except for this point, how will we draw it? Open circle, because it's not equal to. So we'll do an open circle at 2. So when I plug 2 in, what do we get?
2, so that's 2 minus 2, the square root of 0, which is 0. So
Yes.
it's 2, 0.
So it's the same exact point. I'm going to, and you don't have to do this, but I'm going to, just for our purposes, I'm going to put an open circle around it. Okay? You don't have to do that. You can just join it up. That's fine.
And there's another great point on this square root function. It's so at 6.
Right. So let's pause real quick. I suggest you then go to that other endpoint and graph that. So you choosing 6 is a good idea here. So go ahead. So 6 minus 2 is.
So 6 minus 2 is 4.
Uh-huh.
The square root of 4 is 2. So
Right.
6 is 2.
1,
So that
2,
means
3,
because
4,
we know
5,
the
6.
shape-
1, 2.
Because we know the shape of a square
Oops.
root function, it should be about like that. It's like a little check
Yeah,
mark.
little curve there. Now, don't forget open circle. I accidentally filled in my point there a little bit, but you can still see it's an open circle somewhat, right? And so then, yeah, you can just join it. Your choice, if you want to, like another good point we could pick, what's another good x value we could plug in here that would be, easy to calculate? 3. Yeah, 3. 3 minus 2 would give us 1. Square root of 1 is 1. So 3, 1 would also be a point. So 1, 2, 3, 1. We could put that point. And that would be a solid dot because it's in the interval there. So we'll just connect them. And then voila. There's our little piecewise function. Okay. There's our little piecewise function. Okay?
It's a bounce.
Yeah, it does look like a little bounce.
For a check.
Okay. Or like, yep, a check too. Mm-hmm.
The ball.
You get all sorts of interesting kind of graphs with these piecewise functions. You can see some below there. There's some already graphed and stuff. So you get all sorts of interesting things. All right, so on the front, then, let's have you all try number 1. Okay, go ahead and give number 1 a try. Okay, on your own. I kind of like bled through a little bit with my marker, but I think I can still read it okay. Okay, so give number 1 a try. See what you can do. And I will do it as well here. And again, if you see yourself breaking that vertical line test, you know you're making a mistake, right? So it should not break the vertical line test. Now granted, these ask if they're a function or not. But I believe these all are supposed to be functions. I would only suggest though, so it's at 1. So it looks like you're using the y-intercept there, but if the y-intercept would be an x value of 0. So you only want to use the part of your line that's greater than or equal to x value of 0. So here's x equals 1. So we're going to start here. Okay, so don't use that. Yeah, exactly right. A whole doesn't count as a point. So it would be perfectly fine. And then you're going to go to the right of to the left, I should say, and so you're not going to have a line beneath it anymore. So if you just so grab what you got right here. So I would suggest start with this and start with x equals 1.
But this just doesn't apply to that. This doesn't apply to this one.
Well, I want you to graph it first, and then you can evaluate these functions if you want. Right, -2 would apply it to this one. So you plug that in. Well, you don't. You only evaluate it where it's appropriate to evaluate. That's all you do. Okay? So let's see. So we start at 1. When x is 1, 1 times 2 is 2, plus 1 is 3. So it should be 1, 3 is where your first place is, and then you want to use your sloping interval and flow like that. Okay? Good job, Dan. May, looking good so far. Looking good so far. Good. Okay, you're evaluating first. Okay, you can do that, but again, just figure. Take this first piece here. Start at 1. Plug it in. 3. So plot a point. 1, 3. On your graph. Okay, just like that. And so then, now you can use, since this piece is going to be true for all x values greater than or equal to 1, that means to the right, of 1. So you can just use your slope, 2 more points if you want to, up 2, right 1, up 2, right 1 if you want, or you can plug in more numbers if you want to check 2. Okay, pretty good here, except remember it's at x equals 1 where these change over. You have it at 0 where they kind of switch. X equals 0. So at 1. So you just erase this part of your line and then extend this up to that 1. That's all you got to do.
I see my mistake looking at her work.
Okay.
But may I go to the bathroom?
Yeah. That's fine. Jen? Well, what's the x that you're plugging in here? -2. So according to your piecewise function, which part would -2 go into? Just the bottom one in that case, right? Well, looking good. Good job. Close, but the point here, these points aren't going to join up because we plug 1 in. 1 squared is 1 plus 3 is 4, so it's 1, 4. So it's going to be just a bit above, like you can see here. Okay. Chrissy, how do you do it? Okay, so you got 1, 3, which is the first point of this, but then don't forget to get more points here. So like from this point, you can use your slope and go up to right 1, up to right 1, getting more points because you're going to go to the right, right? X is greater than 1, so go to the right of that. And then for things to the left, well, you're going to start with 1, plug it in there, open circle though, and then proceed kind of thing. So those little calculators beneath there are just for like extra practice. So now all of these should be filled in. This was open because x is less than 1, so we're not going to equal 1, we'll have an open circle. But everything to the left of that is still okay. So these are all filled in, and then just connect the dots as you go. So you fill out these are all filled in circles, except for that. Yes. Yeah, and then an arrow at the end. Yes, because only at 1 are we not equal to 1, but everything below that is okay. Yeah. Yes, exactly. Does that make some sense? Yeah, this one's good. Okay. All right. Yeah, you got it. You put an open circle there if you want. And the quadratic. Not all of them. So you only connect the parts that are supposed to connect. So like this, anything with this can connect. So from the 1 up like that, you can connect that. That's the line. And then this part of the quadratic you can connect too. So I would start with like I actually start with plugging 1 in here. 1 squared is 1 plus 3 is 4. So I would call the point 1, 4, but make it an open circle. Okay. All right, I'll show you here. So this is what it should look like. Okay, something like that. I use the scale of 1. Okay. I think I see what some of you guys are getting stuck on here, and so let me just quickly say these function evaluations here. Okay, these weren't meant to like give you all the points you needed to graph it. This is more just like, hey, here's some practice with evaluations. Okay, you're going to use your own kind of. I mean, you can use some of these points if you want to help you with graphing, but really the graphing part is like what I was saying earlier. Okay. Like for this first piece here, start with 1, plug 1 in. 2 times 1 is 2, plus 1 is 3. So 1, 3, there's your dot right there. Okay? And then if I want to graph more of this, what kind of x value should I plug into this to get more of this graph?
Ones that are greater than or equal to 1.
Exactly. So anything greater than or equal to 1. So 2, 3, 4, whatever you want. You can plug those in, and then you get more of your graph, and you can see, okay, it starts here and then goes off, okay, to the right. Then for x squared plus 3, again, start at 1. I know it doesn't have an equal to. That's okay. We'll put an open circle. Start at 1. 1 squared is 1, plus 3 is 4. 1, 4, open circle. And now, to get more of this graph, what kind of x values do we want to pick? Stuff that's less than or lower than 1. So 0, -1, -2. And so I did 0, there's -1, there's -2, and then just connect those dots, and again, arrow in that direction. Okay? And that's how you complete the graph there. Okay? So it's more to keep track of than what you're used to with graphing. Okay? You not only have to worry about graphing correctly, but also then staying within your constraints. Graphing this correctly, staying within the constraints. Okay? Just like that. All right. Further questions on that? Go ahead, question?
What about the second?
Number 2 and number 3? Or these parts right here? So, f of -2. Well, again, use your piecewise function to guide you. Which part of the piecewise function are you going to evaluate -2 in? The second one, because that's an x value of less than 1. So you get 7.
Yeah.
Does it make sense? Or so negative 2, plug it in for the x. Negative 2 squared is 4. Plus 3 is 7. You don't have to graph that. I mean, that one does fit. So there's negative 1, 2, 1, 2, 3, 4, 5, 6, 7. There it is. I did graph that point. But 613 doesn't. So which one's closed circle? This one?
Yeah.
So this one's closed circle because x is less than 1. It is a point. All right, like this negative 2 is less than 1, so it counts as a point. But at 1, there would not be a point, it would be an open circle. But that's where you want to start, though, because you want to count all the values, just to the left of 1. Okay? Question? I can. Yeah, I can. Okay. So let's have you guys try 2. Yeah, go ahead and try number 2. Okay, try number 2 then. Give number 2 a try. This one might not be a function, so let's see here. So at negative, so you started with this one, right?
Yeah.
So negative 2, plug it in. 4 plus 1 is 5. So at x value of negative 2, you should be at 1, 2, right?
Oh, I meant to put it equal then.
So you should have the point negative 2, 5.
Yeah, I did.
Okay? So then that's going to be an open circle.
Yeah,
Right.
it's actually an open circle.
I'm not saying it's not. I'm just saying I'm just confirming that it should be. Are you kind of to this? Okay. And then so we want to go greater than. So to get more of this graph, we have to pick x values that are greater than negative 2. So you pick like negative 1, 0,
So I use
1.
this.
Okay, 8. That's fine.
So
It's kind of hard to get to it, but yeah. Okay, and then so yeah, you want to connect then your I think this point. Right, because that's at 5, right?
Connect this to that and then that.
So yeah, these two should connect right here because they're both part of this graph. So that should connect to that, right?
Yeah.
Okay, because they're both on the same part of the graph. If you need more points, you can also plug in other x values here. You don't need to use these. These are just like for evaluation part. You can pick whatever x values you want that are greater than negative 2. So you can just pick like negative 1 or 0 or something like that, and plug those in and get their matching points.
So now it just okay.
Okay.
Yeah, but
So there's no one. It's not a function.
Yeah, if you connect it, it should be roughly okay. Question again. Okay. And then at exactly negative 2, you have the y coordinate of 1. So at negative 2, 1, that'll be a filled in point. So you got that. Okay? No connection though. No connection. It's just a point. Floating in space right now. Floating in the coordinate plane. Okay? Then we'll go to this piece. Start at negative 2. Negative 2 plus times 3 is negative 6. Plus 11 is 5. Right? So you have negative 2, 5. Same point. So that's what your starting point for this here as well. Open circle then. Right? So right there is where you're going to start. Let's pick another point. Well, you got to pick some other x values that are less than negative 2. So like, I guess you use the negative 4. So negative 4, negative 12, plus 11 would be negative 1, right? There you go. So negative 4, negative 1, 2. So you're going to connect this and that. And then draw through 2 as well. Yeah. Yeah, we can do that. Yeah, it's not a problem. It's just a single exact point. So that's about it. So let's go through. Let's talk about number 2. Okay, you've had a chance to look at it here. All right. So number 2. I'm going to start by graphing this top piece here. All right, this top piece. What x value should I start with here for this top piece? Negative 2. So I'm going to plug negative 2 in. Times negative 2 is 4 plus 1 is 5. So negative 2, 1, 2, 3, 4, 5. What kind of dot should I put here? Open circle because it's not equal to, right? Okay. Now, I have not finished graphing this yet, right? I'm going to graph this thing for x values greater than negative 2. So what other x values can I choose to plug in here? 0, negative 1. 1, 2, 3, 4, whatever you want. So I'm going to pick 0 here just to make it easier. So, and I'll get to your question, Jenna, in a second, okay? So let's plug in 0. 0 times negative 2 is 0, plus 1 is 1. So 0, 1. And this now is a filled in dot or an open circle? Filled in, right? Okay, Jenna, what was your question? Sorry.
Wait, I'm just confused on how we started this.
this is the kind of like the constraint on this graph, right? We're only supposed to graph this for x values greater than -2. So I'm going to go up to the edge, the boundary, the border of this part of the graph. And so it's -2 is where we're going to start.
So you haven't done anything with the 1 to 4 yet?
I have not started with either of these two pieces yet. Yep. Okay, and in fact, I would suggest you only focus on a piece at a time here. Okay, so pictures? Gotcha. All right, so 0 plugged in gets you that, and you get the idea from there, right? You can get more if you want to, but we can just kind of connect the dots and see, okay, it's going to keep going like that. Okay? The homework will be on Google Classroom, okay? Adrian will be on the Google Classroom. Okay? So that takes care of that piece, right? X greater than -2, we're just going to go to the right there. All right, next piece. At -2 precisely, what's our y value? 1. So -2 up 1, circle or fill it in? It's equal to -2, fill it in, okay? Solid dot, okay? That's all you have to do to graph that. That's all there is. All right, x is less than -2. So again, we'll start at -2. We're going to plug it in here. -2 times 3 is -6, plus 11 is 5. So -2, 5. Oh, we're back to this open circle. Okay? But now we're going to pick x values that are less than -2. So like -3, for example. -3 times 3 is -9, plus 11 is 2. So -3, 2. Okay? You can plug in, -4. -4 times 3 is -12, plus 11 is -1. So -4, -1. And you kind of get the idea. You can then just connect the dots in the opposite direction there. And so there's the graph. Okay? There's the graph. Okay. Is it a function still?
Yes.
Yes. Yes. Okay. Any vertical line you draw will only intersect the graph at one point. All right. Questions on any of that? So we didn't quite get to the writing the equations of piecewise. We'll get to that tomorrow. I'd like you to try and finish this one up, okay? So that way you can see how it is. And I think there's some additional assignments for homework too. Okay, so but I suggest you get some practice with that. Yeah.
So I still think I need some more help, but since I have an extra half milligram of resveratrol on me, I don't think it'll be much use today. So could you sign me up for tomorrow?
So here's the other thing, folks. I won't be here tomorrow, okay? I have a meeting I have to go to.